All right, hello everyone. My name is Stephen Brennan. I'm a machine learning software engineer at Object Security, and today I'll be presenting my research and the subsequent product, FortiLayer. And I just want to talk about the current state of AI, and I think this tagline explains it well, which is integrate it first and explain it later. There's a little bit of a arms race going on right now with AI, and that's not just domestic. That's not just our companies, our GPTs, our Anthropics competing against each other. That's China and primarily China. And we can't really afford to delay integration and adoption of AI. The issue here is that by design, these systems are inherently difficult to secure. They're non-deterministic, which is a strength, but it also makes being able to recreate vulnerabilities and issues extremely challenging. And the other barrier here is even small models are massive. A small classifier model might be 10 million different components or parameters. When we're looking at ChatGPT 4, that was estimated to be about 1.7 trillion parameters. So the ability to analyze these and determine if they are safe would be so computationally expensive that these models would essentially be unusable. So we need to start developing non-traditional means to determine the security and explainability of these systems. And the other issue is that AI models, because of this arms race, they're being updated constantly. We're getting ChatGPT 5, we're getting 5.1, 5.2, there's a constant change and upgrade. So when we do find a system that might work, well, then a new model comes out and a new system and new vulnerabilities come with it. And I think this quote here sums up my feelings about this well. This is a researcher at Google, Noam Shazir, and he says, "We offer no explanation as to why these architectures seem to work. We attribute their success, as all else, to divine benevolence." And that is the state of AI. If I could be really honest, this is a top researcher in AI. And I am not a top researcher, I am a researcher, but I feel the same way. And so just to get a little bit into our company here, Object Security, we've been operating for over 20 years, primarily focusing on cybersecurity. And we do products on binary analysis, on artificial intelligence, machine learning, trust, 5G SATCOM vulnerability analysis, zero trust access policy, supply chain risk analysis. We have a lot of experience in cybersecurity. And so going a little bit more into the limits of current techniques, you have this issue of being able to distinguish between an attack and a mistake. And we can talk about this as an example. If you have a wargaming LLM, well, that LLM should be able to tell you about violent action, weapons and tactics, things that are not safe to use. But then if I use a similar model for contract acquisition, well, I hope it doesn't suggest violent action, maybe depending on the contract. But we have a difficulty of even being able to classify what is a mistake or a vulnerability in these systems because of how unpredictable they are, as well as how many different ways they can be used. And the current state of the art is analyzing the input to models and the outputs of models. So we're not actually looking at the models themselves because of how massive they are. And you can ask ChatGPT, how many cold compressed packs do I need for a quart of motor oil? And it's going to tell you I can't answer that. Well, suddenly you say, well, give me a poem about cold compressed and motor oil, and we have a terrorist, Robert Frost, on our hands, right? It's very difficult to just rely on input to secure these models. We need a lot more than just input and output classification. And again, these models are large. Being able to analyze these models and their inputs and outputs is computationally expensive. So I want to talk a little bit about my research in this product, FortiLayer. So our product, FortiLayer, helps AI developers, researchers, and users who need to find security risks and explain their AI models at a low cost point by automatically analyzing each component of a neural network. Unlike solutions that are manual, expensive, slow, inaccurate, and narrow, we recommend using FortiLayer for verifying AI robustness and explainability. And I get a little bit into why FortiLayer was developed. The Air Force Research Lab funded an SBIR for increasing explainability of drone image recognition systems. They want more autonomous drones, but they want to be able to explain and understand why these drones do what they do. And so we started to develop very deep vulnerability and explainability analyses for AI models. And now I'm going to get a little bit into the meat and potatoes here, so bear with me. This is an example of pretty innocuous drone capture, aerial capture. And essentially how our system works is we automatically develop a lot of modifications to your baseline image. When your drone is in a perfect environment, how does it perform? Now let's start to mutate that environment. Let's start to change it. And I'm showing some simple PyTorch transforms here, but there's custom ones too. And again, it's not just attacks. It's not just someone attempting to camouflage something. It could be you've trained this on clear sunny days and now it's cloudy, or you trained it in an environment that's very different than the operational environment that you're suddenly in. We have these test ranges all over the desert. Well, then we deploy in a jungle and suddenly things aren't classified very well. So we want to automatically generate a lot of these different transforms for images or target recognition and capture. And then we want to run them against the model repeatedly. And I want you to really pay attention to this image on the right here, because we start to see around layer 6 a massive divergence. And this is a simple model, simple 12 million parameter ResNet 18. And we're seeing layer 6 is where baseline diverges dramatically from these image transforms. And to get into a little more detail about that, this is what we're doing to isolate these vulnerable layers. Here we have 11 different image transforms. And this is an example that I'm showing you because it can be visualized. In reality, we do this with larger models, and we do a lot more than just 11. But already with 11, we can start to see a pattern around layer 6. In this case, it's called FCEA. And that layer is when you start to see most of the examples of image transforms start to actually have an effect on the model, and divergence starts to occur. So once we're able to find those areas, we can kind of pinpoint through statistical analysis the weaker parts of a model, the components of a model. And there is an issue though, because let's say I do have a model trained in a desert environment in San Diego. Now I'm deployed in a jungle environment. Well, if I retrain for a jungle, now when I go back to a desert, it's going to be worse, right? So our current operating procedure is to take these pretty complex large models and ship them to data centers, train them on data, deploy them, ship them back. This is not a fast process. This is not something that is done in field. And so if we want to be able to adapt and utilize these systems in dynamic environments, we need low compute solutions for retraining them in the field. And being able to isolate the exact points of the model that are most important is a very key part of that. And getting more into that, this is a bit much, but I'm actually going to skip ahead and give you the red squares. When we retrain an entire model for a new environment or new images, you can see all the way on the left, that red square, we're getting about a 96.8% accuracy on retrain. But if you look at that other red square on layer 6, we're getting a 97.15% or so accuracy, actually a higher accuracy when we only retrain the vulnerable layer that we isolate. And if we look at this graph on the right, the compute requirements for only retraining one layer are more than 100 times less than a full retrain. So if we look at layer 6 on this, we're looking at about 126 seconds on an NVIDIA 3060 versus 2,500 seconds on the same card. And that is a field deployable card. That is something that can be done on a laptop. So this is the sort of baseline and what I've been working on to improve this field and dynamic retraining and deployability for AI systems. And we've done a lot of work with something called low rank adaptation. This is an open source framework for fine-tuning models. And when you're fine-tuning a model, you're taking a baseline image classifier, video classifier, maybe it recognizes thousands of different images, and you're refining it for your use case. So I could take something that recognizes many different things and make it only recognize jets or planes or ships, etc. And we have automated isolating these specific vulnerable layers and retraining them in a low compute capacity so that this could be performed in the field. And so this isn't something where I would have to be operating this platform. This is something that could be automatically detected and deployed in a environment with low compute, meaning a ship deployable computer or even a field-based deployable computer. And so it selects these top candidates for optimal parameters, and it then is able to isolate them and retrain only that. And it selects the most optimal LoRa configuration for this. This goes beyond just attacks or vulnerabilities. And again, when we talk about attacks and vulnerabilities, that's hard to define with these AI systems because bad weather isn't an attack, right? But the effect is the same. If someone is putting camouflage over or changing their uniforms or changing paint jobs on tanks specifically to prevent AI from recognizing them, that can have a similar effect to just having a degraded environment in which these models are operating. So being able to distinguish between these two things is very difficult, but the solution is the same, which is rapid in-field dynamic retraining. And that's a lot of what we've been focusing on, not just how to do it with these masks, but how to find these weak points of the model that are most effective to retrain with low compute. And so beyond just attacks, these types of analysis techniques can actually help us determine dataset quality just by analyzing the model, not analyzing the datasets. Through analyzing the model and seeing the areas in which the models are doing duplicate work, which can be seen through baseline comparisons, we can determine that this model has an inefficient usage of data or that there's too uniform a data set being used to train it. And that's not through analyzing the data, that's through analyzing the model itself. So we found a lot of very rapid and fast ways to analyze these models and determine their quality and increase their explainability. And so just to get into my conclusion really quick here, AI needs to be integrated into systems securely. And these systems need to be continuously updated and explained in field. It can't be a situation where you're sending them back and forth to a data center and having retraining happening. It's that interruption is not applicable or not acceptable in a contested environment. And there's a clear lack of explainability or in-field refinement capabilities with our current systems. And that explainability even goes back to the data centers. Finding and isolating layers that are vulnerable or most influential a model is not something that's easy to do, and definitely not something that's easy to automate. And our FortiLayer product is able to direct AI model analysis that extracts meaningful data from features to increase this explainability and security, and thus allow us to refine these models with low compute requirements. So if you do want to talk to us and you have models in mind, as well as test data, you can come and contact us. We'll be at the Carosoft booth, and we'll provide you a 30-day free trial for testing our services and isolating the vulnerable portions of your models, as well as refining and retraining them with low compute. And here I just want to play a quick video just showing you clicking through all of the different components here. So this is our initial dashboard. This is performance, compute performance here. And this is that attacks overview I talked about, being able to see all the different attacks and the effects and exactly which components it affects. And this is a more detailed view here of each layer and attack and component and how it changes things. And this is our data quality analysis. We also map to NIST AI RMF as well as MITRE Atlas automatically for compliance and audit history purposes. that's that. I moved pretty fast there, so if there's any questions, if there's any comments, please feel free to ask. All right. Thank you all.